Hello, welcome to my talk on boundary element method for wave energy conversion, part 5, the examples and applications. This is the last talk of the series talks on this topic. In here, I will very briefly introduce the famous boundary element method code, including Wamit, the most famous commercial software for wave structure interactions. Nemo, the well-known open source. And HAMS, the in-house code, which can be available free of charge on request. For the open source, a short introduction is also made on how to successfully run Nemo. Use the provided examples as the first impressions of the open source BEM code. Followed are two simple examples for different wave energy conversion principles: a bottom fixed point absorb and a fixed oscillating water column wave energy converter. These two examples are used for two purposes here: to show how to use the BM results for studying wave energy conversion, and to compare Wamit and Nemo in different applications. Wamit is the most famous commercial boundary element method for wave structure interaction, with some unique functions for practical applications. For instance, the inclusion of the thin structures, the suitability for oscillating water columns. In fact, Wamit is an industry standard for studying the hydrodynamics for the offshore platform. To run Wamit, there are 4 basic files. The first file is the configuration file. So in this file, you can decide whether the low order or the higher order would be used, whether the potentials need to be solved, and what is the method for solving the simultaneous equation, direct or interrelation. Setting the form of the potential, POT, and the force control file. The potential setting file. Here, the panel file must be specified, and what depth would be specified, and whether we need to solve the radiation or diffraction problem, setting the wave period or wave frequencies, and the incident angle of the wave, and the setting of the motion mode. And we need to specify the force control file, FRC, for the force and the motion calculation. So the output would be given for added mass, damping, wave excitation, response amplitude operators, field pressures, velocities, etc. Here, the center of gravity must be given. The radii of the generations need to be specified, and the field point need to be specified if we need to look at the problem. So the output of Wamit include the file .1, for instance, cylinder .1, contains the added mass and radiation damping coefficient. .2 and .3 file are for wave excitation, but in different methodologies. .4 is a file for response amplitude operator. .out is the output file of Wamit, which contains outputs from Wamit.
and .hst contains the calculated hydrostatic coefficient. It should be noted here, WAMIT outputs are all given in dimensionless forms, but the displacement and the center of buoyancy. Nemo may be the first open source for wave structure interactions, which can be downloaded from the website. The open source packages includes the boundary element source file in Fortune 90, the executive file, including preprocessor, solver, post-processor, and the mesh, and the file for running Nemo. The best method is to use the MATLAB script Nemo.m. To run Nemo correctly, the file Nemo.core must be set properly based on the actual problem. This file includes the environment for modeling, including water density, gravity acceleration, water depth, and the wave measurement point. The floating body descriptions for single body or multi-bodies, including the panel files and the numbers of the points and the panels, to specify the calculating modes of the motion and the forces, moment, and the relevant coordinates. For the local cases for solutions, including the wave frequencies and the wave directions, and the parameters for post-processing to calculate the impulse response function, IRF, to calculate the pressure, to obtain the Cauchy function, to get the free surface elevation, etc. So generally for wave structure interaction, we have the linear dynamic equation for the rigid body. Nemo could provide the added mass here, Aij, the damping coefficient, Bij, and the wave excitation, Fexi, while the mass matrix and the stalling coefficient must be calculated based on the floating structure. In the past few weeks, I have been asked to make an introduction on how to use Nemo. Basically, this is a very large topic and there will be lots of details to be discussed and thus lots of slides to talk about it. It would be beyond the scope of this talk. However, here I would like to show a very simple way to run Nemo. Use one of the provided examples. Take the example of two bodies. I will show the run step by step. This would be very important if you can run Nemo for your first example. Then you will understand Nemo better. Now suppose you have downloaded the package from the website. So the step 1 is to unzip Nemo into a folder. Here I use the default folder, a weird name, but you can change the name as you wish. So in this folder, we can see some files, including introductions as well as the license description, and some photos, including the source code and the executables. Here, we are only interested in the folder MATLAB routines and the verification. And in this folder, we can find some examples for Nemo runs.
The second step is to go to the validation folder and choose the example 2 bodies. In this folder, we can see only 2 photos and some files. Here, 3 important files are cube.dat and rotated_cube.dat are the files contain the panels for the 2 bodies. And the file Nemo.core is the file for setting the BEM modeling. Details can be seen later. Now if we copy all the files in the folder MATLAB routines into this folder, and we can see some new folder and files in this folder, highlighted in light blue. Now, all the executables are in the folder Nemo here, and the 2 MATLAB scripts, Nemo.m and fd2td.m. Nemo.m reads the set from Nemo core and run Nemo, while fd2td.m would be used only for the transform from frequency domain to time domain. So after the copy, we are almost ready to run Nemo. Step 3, we need to build a very short MATLAB script named Nemo_non.m. So in this MATLAB script, there are only few lines here. The wave frequency would be given as in this form, and the wave direction given in this, and the water depth given by this. Here, water depth equaling to 0 means in deep water. So step 4 is to run MATLAB script Nemo_run.m. As expected, we will see the information showing the progress of the Nemo running. In the summary, we can see the water depth is infinite. It contains 19 wave frequencies from 0.2 to 2.0, and 1 wave direction, 0 degrees, for 12 radiation problems and 12 forces. After the initialization, Nemo will solve the problem one by one. Here we can see total 247 problems. This can be calculated by the frequencies times the radiation problem plus 1 diffraction problem, and time the wave direction. So we got 247. And when all the problems solved, Nemo would save the data, and then Nemo run is finished. In the step 5, if we go to the folder results, we can see 1 folder Aqua Plus and some files. All the files highlighted in the light blue are generated by Nemo, while the first 2 are the files only used for the comparison. They are not generated by Nemo. Here, we can see all different files for different parameters. For instance, CA.dat contains the radiation damping coefficient, while CM.dat is for the added mass. Generally, it is not easy to get the relevant information from all these files, unless you have some specific software packages, for instance, TechPlot. Instead, if you are only interested in the hydrodynamic forces, the added mass, and the radiation damping, we can save them directly from the Nemo.m, and the format, the added mass A would be in this form. Here n is the number of the wave frequencies. I prefer use the way I save the hydrodynamic forces. Hopefully, this is your first successful run for Nemo based on the provided examples. But if you would like to run your own applications, you may need to do the following jobs. Building the panels for your own problem. You may use the mesh file provided in the Nemo package, or you can build the panel generation yourself. Set up Nemo Run by modifying Nemo.core for your own problem. But it should be noted, when you modify the Nemo core, you should keep the format of the file. Calculate the mass matrix and the restoring forces for the floating structure if you need to calculate the motion of the floating structure. And use Nemo outputs, for instance, the added mass, the radiation damping coefficient, and the wave excitation to build the dynamic equation for the structure motion and other analysis. In this slide, an in-house BM code for wave structure interaction is introduced. HAMS is such in-house software package which is developed by Dr. Ying-Yi Liu at Kyushu University in Japan. The in-house code is available on request, free of charge. In HAMS, the function for removing the irregular frequency is implemented as that in Wamit. Nemo has no such function. HAMS has a faster computer speed than Nemo and is comparable to the commercial codes as claimed by the developer. The ongoing development with more functions and improvements being added, but Nemo seems to stop updates since 2017. Possible communication directly to the code developer, Dr. Liu. And the author believe HAMS has a better green function computation for better BM modeling. See the open source ThinGreen 3D. This is a very important feature for a BM code, and we will see this as that in Wamit, while the open source Nemo has a limit in this regard. The author would like to thank Dr. Liu, who sent me a copy of HAMS code. However, the author did not find enough time to learn and use the software for this talk. I hope in future I will make a detailed comparison for this BM code. The first example is the bottom fixed point absorb. This may be the simplest wave energy converter, which uses the heave motion of the float for wave energy conversion. In reality, we have seen such practical wave energy converters. For instance, core power, see the drawing. Another famous device in this category is the sea-based wave energy converter. See the website for more information. Here, we will look at the description of the device first. A relatively shallow float connected to the power takeoff system, which is connected to the seabed. The buoy would move up and down under the wave action, so to drive the PTO to generate power. That is, the wave energy extraction. Principally, the buoy may have other motions such as surge and pitch, but these motions have little influence on the wave energy conversion. Thus, for simplification, only heave motion is considered here. This point observed in this study has a diameter of 6 meters and a draft of 1.5 meters. Such a device would have a displacement of 42.41 meters cubic, and the water plane area as it's 28.27 meters squared, and the restoring coefficient for the heave motion C33 would be given as this 284.2 kN per meter. And this buoy has been examined in this reference. The natural period of the float is 3.49 seconds, or a frequency omega 0, 1.8 radians per second. The power takeoff system would be considered as a linear damper power takeoff. The power takeoff force would be given as FPTO proportional to the float's velocity. For using BEM to study the hydrodynamics of the float, the first step is the panel generation. See this plot. The wet part of the truncated circular cylinder, and the panel can be seen in this plot clearly. In the definition of the panels, their normal vector point out of the body. See here, the normal vector is pointing out of the screen. The lower order quadrilateral panels are defined with 4 vertices for each panel, and the order of the vertices are determined using the right-hand rule. See here. Fine panels should be generated near the corners and near the free surfaces. For this example, we have total 1,208 panels, and we use these panels to calculate the displacement. It would be 42.29. It is 0.28% less than the accurate displacement. And the restoring coefficient C33 would be 283.4 kN per meter. Again, it is 0.28 less than the accurate value. Here, we show the comparison of the hydrodynamic forces using Wamrit and Nemo. For radiation problem, the forces would be given in terms of added mass and the radiation damping coefficient, and for the diffracted problem, the wave excitation. In the comparison, we can see for this example, Nemo and Wamrit gave very close results. Only some small differences can be seen. For instance, Nemo had large spikes than Wamrit. In the radiation damping coefficient, Nemo might have a negative damping, the large spike, which is not physically correct, since in physics the damping coefficient must be positive. However, such large spikes might be removed if finer panels are used. Also, such a nano spike might not cause significant problems in structure motion or wave energy conversion. And from the damping coefficient, we can see the max radiation damping happens close to the resonance frequency here, about 22 k Newton second per meter. In Wamit, if we set up the force control fire, then we can calculate the motion response using Wamit directly. However, Nemo has no such option. Hence, we have to establish and solve the dynamic equation for the structure motion. For the heave motion of the truncated cylinder, its dynamic equation in frequency domain can be simply expressed as this. Here, the added mass, the radiation damping coefficient, and the wave excitation can be all calculated from the BM method. It should be noted, in the BM method, the excitation is calculated assume the unit wave amplitude, and the mass of the structure and the restoring coefficient can be easily calculated for the heave motion. So the complex amplitude of the structure heave motion would be given as this expression. This would be equivalent to the response amplitude given by this, since A equals 1 meter. So if we draw out the heave response for this truncated cylinder, we can see both Wamit and Nemo give very close results. The small difference can be seen only at the resonance frequency omega 0 equaling to 1.8 radians per second. And the maximum response is about 2.2. By adding a pure damper PTO, the dynamic equation of the heave motion would be given as this. Here, BPTO is the linear PTO coefficient. Thus, the motion amplitude of the structure with the PTO would be given as this. And if we choose the PTO damping coefficient as the maximum radiation damping coefficient 25 kN second per meter, so we have the response as this, and the maximum response now is about 1.1 rather than 2.2, as we seen in the previous slide. And we can calculate the average power based on the solution of the structure motion with the PTO. So the average power would be given as this, and we can do some mathematical manipulations. We can have the expression as this. So for the same PTO, we can obtain the average power showing here. So we can see the maximum power conversion is about 42.5 kilowatt, and the maximum power conversion happens at the natural frequency of the device. You can see omega 0 equaling to 1.8 radians per second. The second example is a fixed oscillating water column wave energy converter. This is a cylindric OWC, which is especially designed for studying OWC wave energy converter. This OWC is fixed on a fan which sits on the tank floor. The cylindric OWC has an overall diameter of 0.3 meter and a water column of a diameter 0.108 meter and a draft of 0.3 meter. The OWC float has a displacement of 0.0186 cubic meter. See the half of the float and its panels in gray. In numeric studying the OWC wave energy conversion, an imaginary piston of a draft 0.1 in green is built to represent the water body and its motion. As shown in this reference, the length of the piston can be taken as any value between 0 and 0.3. Generally, if the piston is short, its corresponding added mass in this case would be large, so that the overall mass for the piston would be constant. The details can be found in this reference. For the hydrodynamic study, we can calculate the hydrodynamic parameters for the flow, the added mass, the damping coefficient, and the wave excitation. Here we can see Wamrit and Nemo give some different results. In particular, the spikes happen at different frequencies. Otherwise, they are close enough. In fact, these differences are caused due to the internal free surface, the water column in the middle of the float. Otherwise, this cylinder would be very similar to the previous point observed. Here, we can see again the radiation damping coefficient has a large negative spike, which may not be very physical. In this slide, the hydrodynamic parameters for the piston are presented. Here, we can see very large spikes in the added mass, damping coefficient, and the wave excitation. Here, again, we can see there is a very large negative damping coefficient predicted by Nemo, which is not correct in physics. From this example, we can see the significant differences between Wamrit and Nemo result. It should be noted here, these spikes are not corresponding to the resonance of the actual piston motion, but depending on the length of the piston. And these spikes at high frequencies should not have influence on the piston motion and the wave energy conversion. Based on the reference, we can see the Nemo developers have warned that the current version of Nemo might not work for OWC, and the problem might be caused due to the approximation in the tabulations of the green function, while in Wamrit, the green function is always calculated. Hence, we can see a good computations of the green function would be very important for the BEM modeling. Therefore, it can be deduced that the in-house code HAMS could be better than Nemo in this regard, since in HAMS, the green function has been computed more accurately. Now for the fixed OWC, the flow would be fixed. Therefore, the piston heave motion would be given in this form, which in principle is the same as the point of absorb. However, its hydrodynamic parameters, including additive mass, the damping coefficient, would be affected due to the existence of the flow. As such, the complex amplitude of the heave motion would be given as this, and we can draw the response, the RLs of the piston, see in this picture. So we can see here the resonance frequencies are omega 0 equals 5.6 radians per second and 6.3 radians per second respectively. These frequencies are very different from those we have seen in the wave excitation on the piston. See here, the frequencies at about the 9.6 radians per second and 11.5 radians per second. So for the difference in the piston responses, resonance frequencies from Wamrit and Nemo, we may ask a question, which one is correct, or both are not correct. For answering this question, I would say that Wamrit has been validated to be capable of modeling OWC device, but Nemo is not capable due to the limitation in the green function calculation or approximation. For power conversion of OWC device, we need to build the dynamic equation first. By applying a linear turbine PTO, the dynamic equation can be given as in this form. Here, P is the chamber pressure, S0 is the sectional area of the piston. This pressure can be understood as this. When it is positive, it would push the piston down. Thus, the power takeoff force has a negative sign here. For a linear turbine PTO, for instance, the Wills turbine, the pressure and the flow rate has a relation as this. Here, K is the linear turbine damping coefficient. Capital Q is the flow rate. And in here, the air compressibility has been ignored for a simplification. Thus, we have this expression and this. So the linear PTO force can be expressed as this and this. Now we can define an equivalent damping coefficient K0 equaling to K times S0 squared. Then we have the same expression for the PTO force for the point of absorb. Here, K0 is very similar to B PTO. Now the dynamic equation for the piston in frequency domain would be given as this. This is exactly the same dynamic equation for the point of absorb with the linear PTO. So in this regard, the problem of oscillating water column can be solved in an exact same manner as that in the point of absorb. If the damping on the piston motion is taken as K0, given by this. The solution of the piston heave motion can be given simply as this. And if we draw the response of the piston heave motion, if we take K0
as 2 Newton second per meter. It is equivalent to K equaling to 24 K Newton second per meter power of 5. So the average power response is calculated for the unit wave amplitude given as this. However, for a very small model which only used in the tank testing, so the wave amplitude is taken as 50 mm here for the calculation. So the average power we can see here as this. So the maximum power conversion is less than 0.5 watts if we ignore all this spike here in the high frequency region. It should be noted the wave height would be 100 mm. This is quite a big wave in the tank. So for such a small wave energy converter, the wave energy conversion would be small. For this device is less than 0.5 watts. So it would be very difficult to build such a small PTO for converting this small power. This is why in the tank test, a very difficult issue would be the power takeoff modeling. And it would be very, very difficult for manufacturing a real power takeoff system, if it is not impossible. In this slide, a numerical modeling is on the same OWC device, but the power takeoff is nonlinear. In the experiment, an orifice is chosen to represent the nonlinear turbine PTO. This orifice would represent the nonlinear turbine, such as the impulse turbine. Therefore, the numerical modeling based on the Wamit hydrodynamic parameters is in time domain, since the dynamic equation is not fully linear anymore. If we compare the numerical modeling with the experiment data, so this is the pressure response, we can see the experiment result and the modeling are very close. And this is the internal water surface response. Again, we can see the experiment and the numerical modeling are very close. And from the pressure response, we can see the resonance of the piston would be at the wave period about 1.2 seconds, which corresponds to the frequency of 5.24 radians per second, very close to the numerical modeling based on the Wamit hydrodynamic parameters in this talk at about 5.6 radians per second. Hence again, from this example, we can see Wamit gave reasonable hydrodynamic parameters for this fixed OWC device, while Nemo wrongly predicts the resonance frequency of the internal water body motion, the piston. This confirms the warning from the Nemo developer. Nemo might not work in the OWC modeling.